Okay, number 6. So number 6 was define a ring, an integral domain, and a field, and then provide examples of some which are not the others. So yeah, so ring, integral domain, and field are increasingly specific types of algebraic structures which have two operations on them. So first of all, what is a ring? A ring is a set with two operations, and so those two operations can be anything, but we usually call them addition and multiplication. But of course, they don't have to be. The set doesn't have to be numbers. We don't have to be talking about addition and multiplication. We can talk about any two operations as long as they satisfy these properties. So first of all, yeah. So what are the properties that they have to satisfy? So a ring, first of all, if it just has the first operation, then it's got to be in abelian group. So abelian group, of course, meaning that it's closed, it's associative, it's got an identity, and it's got inverses. So in a ring, we call the identity for this operation, we call that, the additive identity, we call that 0, right? And again, that might seem like a silly thing to say, but again, we're not necessarily talking about numbers or regular addition. We could be talking about anything, but whatever that identity element is for whatever that first operation is, we often use this symbol to indicate it, even if it's not even a number, or it's nothing like the number 0. If it's like the number 0 in this key way, that it's the identity for the first operation, then we use the same symbol. Okay, so anyway, that was that went on longer than I meant to. It's also associative. Yeah, so the second operation has got to be associative, and it has to interact with the first operation in this key way, that it distributes over it. And of course, what I mean by that is that if you've got a situation like this, you can rewrite it like this. And the same thing on the other side. So that's what it means to be a ring, that you got two operations. One of them is super nice and abelian and commutative and identity and everything. And then the other one, the only thing it's got to be is associative. It could be really shitty besides that. But they have to interact with each other in this particular way. Okay, so going up the ladder here, an integral domain. An integral domain is where you give a little bit more restriction to what your second operation has got to do. So your second operation has got to be commutative, and it's got to have an identity. And we usually give that second identity a nice symbol. The symbol for the number 1. I'm not going to be fancy. I'm just going to do that. Let me try again. Boom. So again, we could be talking about matrices, in which case that would be the identity matrix, not the identity, not the number 1. But we would use the symbol of the number 1 though, because it is performing the role of the identity in the second operation, which in that case it would be matrix multiplication. Okay, an integral domain is a ring in which, so the second operation's got to be a little bit better now. It's got to be commutative and also have an identity. And then this is kind of the important one. There are no 0 divisors. So what is a 0 divisor? Remember, A and B are 0 divisors. If their product is 0, but they themselves are non-zero. So two non-zero elements which multiply together to make 0. Right? That's what's called a 0 divisor. Now, if you think about rings that you probably are familiar with, like the real numbers or the integers. Well, I guess the integers are in a ring. The rational numbers. Or no, of course. What am I talking about? Of course, the integers are a ring because, well, this is not the order I want to talk about this stuff in, but I might as well. The integers are a ring because with addition it's an abelian group, and you can multiply them associatively, and multiplication distributes over addition. It is also an integral domain. In fact, that's why we call it an integral domain, because the integers are like this. Multiplication is commutative, and there is a number 1 which acts as the multiplicative identity, and there are no 0 divisors. So Z is like that. Q and R and C are all like that. All the numbers are like integral domains like this because there's no way to multiply two non-zero numbers together to get a zero thing, to get to zero. But there are definitely rings that are not like that. For example, so ring, but not an integral domain. Well, here's a good example. How about Z6? And of course, I mean that with two operations, right? So the set of 6 elements, 0, 1, 2, 3, 4, 5, with addition mod 6 and multiplication mod 6. This is not an integral domain because there are 0 divisors. In this world, 2 times 3 is 0, right? And if, different people prefer some crazy variation on like something like that, whatever, however you like to write it is fine. I'm just going to say 2 times 3 is 0. So this ring does have integral divisors. There are 2 non-zero numbers, which when you multiply them together, they make 0. So 2 and 3 are 0 divisors. And that is, you might imagine, that is not unrelated to the fact that they are divisors of 6. So, yeah. But anyway, integral domain is a place where there's no 0 divisor. So in this particular textbook's version of integral domain, there's also this part to the definition. And so some people, when they were given an example of a ring which is not an integral domain, they gave examples where that part wasn't satisfied, like it didn't have an identity or multiplication was not commutative. I just want to emphasize that different authors define things like slightly differently from each other. The part that they all agree on, what an integral domain, the main piece of what an integral domain is this part, that there's no 0 divisors. Some authors don't require that to be part of an integral domain. Some authors do require it, and they just build that into the definition of a ring. So it's not even a ring unless there's an identity for multiplication. So different people define it different ways. So I would just emphasize that when you're trying to talk about what makes something an integral domain or not, focus on this point. That's kind of the real feature of being an integral domain, and why it's important and why it's even a named category is for that reason, not the other reason. So main thing to make something not an integral domain is if you can find 0 divisors. And then finally, what is a field? So there's a way you can step up from a field from an integral domain. You can say you just take your integral domain, but then make sure you've also got like multiplicative inverses for everybody. Then that's good enough too. My favorite way to define what a field is it's just a ring where you have so for the ring you had the restriction on the first operation that it be an abelian group with the first operation, but for a field you're saying not only is the first operation, when you give it just the set with the first operation, is that an abelian group, but also even for the second operation. Now there's a slight caveat, which is that you gotta exclude the additive identity. So whatever that 0 was from your first operation, you can't do that because that one's not going to have a multiplicative identity. But besides that one, if everybody else has a multiplicative identity, multiplicative inverse, I mean, and this set is now an abelian group as well, well then that's what you call a field. And of course, classic examples of fields are the rationals or the real numbers or the complex numbers, where you got 2 operations, they're both commutative, they both have identities, and they distribute across each other, and everybody has got negatives, so everybody's got additive inverses, and everybody's got reciprocals, everybody's got multiplicative inverses, except for 0. So 0 is allowed to be an exception. Besides that guy, everybody has multiplicative inverses, and that's what makes it a field. So can you come up with an integral domain which is not a field? Easy. Example of an integral domain but not field. How about the very example for which that class is even named? The integers. Of course, the integers are an integral domain, but they are not a field. And why are they not a field? Because they don't have multiplicative inverses. There is no inverse of 3, for example, right? You need a 1/3, and that is not in Z. So yeah, so this is indeed an integral domain, but it does not have multiplicative inverses. So it's like got addition and it's got multiplication. It's like got a lot of the multiplication stuff, but not quite all of it, right? It's kind of so yeah. This is kind of as far as you can go before you have to add in all your multiplicative inverses, and if you do so, well, then that would be the rationals instead, right? And that is the smallest field that you can make from the integers. That's the least amount of things you can add in before you have a field. Does that make sense? I don't know. But anyway, that's it for this one. Yeah, those are your definitions, and those are your examples. Okay.